and especially Andy Wolf for arranging the room and the audiovisual equipment.
Yay, Andy.
And tell you who I am, I'm Alan J Weissberger. I'm the manager of the IEEE Tech Blog, which I'm happy to report is the second most popular IEEE website next to IEEE Explorer. Today's meeting will be in three parts. The first is a conversation with Professor Hennessy about the technologies he's been involved with since he came to Stanford University in September 1977. We'll have a short presentation about IEEE by Tom and discussions with Professor Hennessy, who's an IEEE Life Fellow, on how to make IEEE more relevant to its members and to attract new members. That'll be followed by audience Q&A. So now, John, can you please take the stage and sit in the center? And I'd like to start with a challenge. At our last conversation at a Stony Brook alumni meeting, we're both graduates of Stony Brook University, at that time State University of New York at Stony Brook. We asked Professor Hennessy if he would lead our alumni excursion to Mount Dana and ice climbing the Mount Dana Glacier, and he respectfully declined. So now we're going to give him another more appropriate challenge, because for about 4 years, he rode his bike every day from Port Jefferson to the Stony Brook campus. He became a very, very skilled, experienced bike rider. So we're going to offer him an IEEE expedition to climb either Mount Hamilton or Mount Diablo.
Oh, there we go.
How about that, John?
I've climbed Mount Diablo, so
okay, that's like a 4,000, almost a 4,000-foot climb.
Yeah. Depends on where you start. Since you can drive to the top, it's
That's true.
Okay, so we're going to start with John's move to the Bay Area. He decided after he received his PhD at Stony Brook that he would pursue an academic career. He loved to do research. He wanted to teach. And so he had 14 interviews and he selected Stanford, and he arrived, I believe it was September of 1977. Now at that time, microprocessors were all the rage, but they weren't used in personal computers. They were used in embedded logic. That is, embedded controllers to replace random logic. Apple had just introduced its first PC in 1976, but all the PCs at that time were for hobbyists. It was not until 1981, when IBM introduced their first PC, that it became commercially successful and widespread. So from that period of, let's say, 1977 till maybe 1980, 81, what was your perception of technology in Silicon Valley during those years?
Well, as you said, both Apple and then followed by IBM had introduced products. Moore's Law was in full swing, so the processors were getting faster. There was actually this contest that went on. Intel would announce a processor, and then Zilog would announce a processor, and they'd say, and we have 5 new instructions in this processor. And there was this kind of battle going on. Software was very primitive. What had really transformed and made the PC take off was applications. And the spreadsheets, big breakthrough, because all of a sudden, big improvement in terms of productivity, right? And word processing, of course. There were more primitive word processors prior to the PCs, but the PCs were so much better than the primitive word processors. So that really drove things taking off. And, the fact that processors were getting faster at a rapid rate enabled you to think about more and more applications at the time. Nobody, I don't think anybody had ever, at that point anyway, had said, what's going to happen over the next decade or so? The answer was microprocessors were going to wipe out the rest of the computer industry. But nobody quite saw that happening at that point. Because obviously, if they did, then companies like DEC and IBM would have gone in a completely different direction than they ended up going. But it became clear by the mid-'80s that it was really going to swing.
I was at National Semiconductor Microprocessor Group. In fact, I was the application engineering manager for the microprocessor group at National, and then at Signetics Microprocessor Group. And then during those years, up until maybe 1980, the word on the street was microprocessors are for embedded logic, embedded controllers,
Yeah.
and
Lab
the
kind of
PCs that we have now are for hobbyists. But no one really at that time realized the advances in Moore's law and in N-channel MOS technologies.
Yeah. I mean,
Now,
you have to have the picture of the valley at that time. There are semiconductor companies. There are, HP builds computers, but only for kind of laboratory kinds of environments, right? Control things.
absolutely.
Tandem had just been started a few years earlier. But if you wanted to talk to the movers and shakers in the computer industry, you got on a plane and you flew to New York or you flew to Boston, because that's where all the action was.
Yeah, and Boston was the center of the mini computer industry.
Yeah.
With DEC and Data General and Honeywell and Prime and many others. Okay, so now you're a few years at Stanford and you realize that VLSI technology was coming of age. It was also a shift from assembly language, which was my bread and butter, to high-level languages, because compilers had advanced considerably. In addition, you were influenced by your Stanford University office mate, Jim Clark, to do a rethink of computer technology. How did that transform itself into the MIPS project that you started? And by the way, this MIPS project at Stanford I only found the name out yesterday. It was called Microprocessor Without Interlock Pipeline Stages. MIPS for short.
Yeah.
Is that correct?
Double entendres. We like double
That's
entendres in
right.
academia, it's kind of so Jim Clark had come to Stanford to really try to take advantage of this VLSI breakthrough, the fact that Silicon Foundry, there were no Silicon Foundries quite yet, but they were contemplated. So he had come to Stanford to try to build high performance graphics, and his goal was to replace the Evans and Sutherland machines, then the high-end graphics machines being used for 3D design, which cost about $100,000 a seat, right? And we're done with MSI technology. His goal was to build a back-end VLSI pipeline for graphics, became the geometry engine that could do that function. So he did the project. I helped him. I actually worked on and built software for the project. I built a thing that would generate the microcode for the project. And then he spun that out. And so we were saying, okay, we still got money to fund this VLSI research. We need a new project. Let's do a processor. Partly because I had been writing papers on compiler technology and various things. So we started on a processor, and that became MIPS. And it was driven, as you said, Alan. We thought, why compile to an instruction set that then has to be interpreted by microcode? Why not just compile directly to something that could be directly executed by the hardware? And that was the real focus.
So following that, you co-founded MIPS in 1984, and MIPS was a fabless semiconductor company that designed RISC processors, which were sold commercially, and also the IP, intellectual property, was licensed as RISC cores. Tell us about your motivation for starting MIPS, your 18-month leave of absence at Stanford University when you were there full time, and how you got that company going off the ground.
So unlike today's environment where every student wants to be an entrepreneur, I was a reluctant entrepreneur, actually. We published our papers and we thought 4 graduate students built something that's several times faster than commercially available processors. This sounds like it's a great idea. let's go for it, guys. And nobody picked it up. In fact, IBM that had worked on the project actually canceled one of their RISC projects. DEC, Digital Equipment Corporation, had an experimental project they did in Palo Alto at the DEC World Lab, and they decided not to commercialize it. So along came an early computer pioneer named Gordon Bell, who was kind of the chief engineer, one of the chief engineers at Digital Equipment Corporation. And he said to me, he said, if you really believe this technology, you got to start a company. Because this technology, according to the results you have, is too disruptive. People are going to be reluctant to introduce because it's going to wipe out their existing product line. Yeah. So that got me convinced. I called up a former grad, Skip Stritter, who had worked on the 68000, and John Masuris, who was on leave from IBM, working on our project. When IBM canceled the project, he said, I want to go do the startup thing. I'm not going back to IBM. They just canceled the RISC project. So John decided to join us. 3 engineers. We knew nothing about starting a business. And I mean,
And what about fundraising?
Fundraising. Well, I had known the venture capitalists that had funded Silicon Graphics. So I had met them in a few settings. But I mean, I couldn't read a balance sheet. I didn't know what a gross margin was. When they said, well, what's your sales and marketing budget going to be? I said, this product is so great, it'll sell itself. We don't need sales and marketing. I mean, I really naive. Okay. So that later on, that comes back to things I did at Stanford to try to make sure that people spinning out companies from the university wouldn't be so uneducated. But that meant we had to find venture capitalists that would really help us build the company, right? Hire a CEO, think about all that kind of stuff. So we found one company that was willing to put money in. There were a bunch of other companies that passed. All of them came back in the next round, but it took a while. And you know, we didn't have a formal business plan. We had a bunch of slides that showed what we could do and how much money we thought we needed. And that got the company enough money to get up and going. And then we just hired a great team of people. We hired really great designers, and that's what made it really successful.
Tremendous accomplishment since you had no experience in business.
Yeah.
Right?
Yeah. Second time around was a lot easier. I had an idea what I would do the second time around.
We'll get to that.
Yeah.
We'll get to that shortly. So let's talk about the evolution of RISC. When John started MIPS, the target market was high performance workstations. And that went well for quite a few years with Silicon Graphics and others buying the MIPS in either IP or silicon. But later on, Intel came up with faster processors for perfecting their semiconductor processing. And so that market sort of faded away. But then all of a sudden, when the mobile market started to take off, it was RISC again through ARM limited cores. And now you find ARM limited cores or Qualcomm cores, which use ARM, in just about every mobile device possible. Let's talk a little bit about that evolution before we get to the next one.
Yeah. So I think
Evolution from high performance workstations
Yeah,
to mobile
yeah.
cores.
so. The advantage that RISC had was to some extent efficiency. In those days, it was use of silicon efficiency. But at a time when Moore's law was booming, that wasn't a very long-lasting advantage because silicon was not the thing that was in short supply. As things shifted, the first performance-driven market that emerged for the RISC stuff, the first few were games, Sony and NEC, and Sony and Nintendo both built things based on MIPS technology. And there it was about performance for a low power part, a low power, low cost part, because you had a price target much lower. So all of a sudden, efficiency, silicon efficiency becomes really a pressure point.
Well, was it about performance combined with low power?
Yes. Well, low power, yes, low power because they weren't going to put a fan in a game unit, right? They weren't going to put a fan. And then of course when handheld devices came along, then low power became battery life, right? And that really took off. And that's what really made it successful in the end.
So we should take a step back. How many people are familiar with RISC? About 1/3 here.
Yeah.
RISC stands for Reduced Instruction Set Computing, and it has, I think, simpler instructions, but more of them. Can you elaborate on that?
Yeah. So the way to think about this is an analogy that my co-author Dave Patterson came up with. Think about reading something that uses lots of $10 words in it. So you start reading it, and you have to keep going and looking up things and figuring out what those words mean and things like that. Slow reading process. Now, suppose it's rewritten by your favorite large language model and to use only simpler words that you might find. Then you can read it just fine. So that's the idea. You can make it faster by having simpler instructions and a smaller set of them. I mean, what happened, and it happened to the x86 architecture. It also happened to the DEC VAX. What happened was it was easy to add instructions because you had a microcode interpreter. So you just added instructions, and it just grew and it grew and it grew. And lots of those instructions, I remember the days where people working at these companies would hand code things using these instructions. No compiler in the world was ever going to generate a lot of those instructions. But there was this kind of hand coding, I can get this tighter than you and things like that. Well, that disappeared when we moved to high-level languages. So all of a sudden, it didn't matter anymore. And we could clean up and get a lot of performance advantage by getting rid of all that junk.
Right. Okay, so now we're at the point where RISC has to find a new home, and it found a home big time in mobile devices. What was its attraction there? And
Right,
it was ARM limited.
They priced
Intel and
Yeah.
everyone else
Yeah.
tried to get their processor into mobile devices.
Yeah. So it was really priced. I mean, all of a sudden, in fact, when MIPS was asked to bid on the first Nokia, the first phone, the price they wanted on it was so low that MIPS said, we don't think we can build the part for that price. Right now, what we should have foreseen was that the market was going to take over and get so big that eventually you would have been able to afford to do it at that price level. But that was the big advantage: price and power, both. Right, because you got battery-held devices, and
That's the most important.
in the early days, the battery technology was good. Yeah, so that was the so power, efficiency in general, right? Power, silicon use, which determines how much you can sell the part for.
So ARM is.
And then ARM did a great job. ARM built a great ecosystem. They, as people moved into selling cores, so you're selling cores as IP rather than selling necessarily a single chip.
ARM Limited, for those who don't know, is a UK company that I think they're owned by SoftBank now, that license their RISC cores to others who embed them in ASICs or other silicon.
So they sell soft cores, meaning you get the core, you get a description of the core that you can put through a piece of software that will generate the actual hardware, and then you can bolt on whatever else you want. And they built a great ecosystem. So they made it really easy if you were building something to, add a little signal processor on the side or do something like that. They did a really spectacular job of building the ecosystem. And that's what made them really successful.
Okay, we're going to take a step back and then a step forward. The step back is your 1990 book with Professor David Patterson of UC Berkeley. How did you being at Stanford, come to collaborate with the UC Berkeley professor? What research did you do that led up to that book? Yeah. And what was your motivation for doing it?
Well, so Dave and I had both worked on RISC. I mean, we were, in some ways, it was interesting. Separate projects. And then when we were a few years in, we started meeting once a year in the summer to exchange ideas and things like that. In fact, I think we both take the view that, thank God there was another project doing this contrarian thing, because otherwise we would have been steamrolled by the naysayers. And so that was key. And then Dave and I were both teaching computer architecture And we were pretty unhappy with the textbooks that were out there and how it was being taught. We used to say it was a bit of one from do this architecture, then do that architecture. No engineering. Yeah, one from college, one from no engineering framework. Well, computer design is an engineering discipline, right? It's about numbers, it's about evaluation, it's about comparisons. So we decided to do the book together, and we both took some time off and wrote the book. We wrote it in about a year of taking time off.
Was it a successful textbook, both for college students and for practicing engineers?
Yeah, it sold. Microsoft actually put it in their store, so if you were a Microsoft employee, you could get a copy of it. It sold the first year. It sold as many copies to practicing engineers as it did to students.
Thank you, John. That was our step backward. Now we have 2 steps forward, A and B. A is that ARM now has a new target market. New target market is compute servers in cloud resident data centers. According to the market analysis that I read, they now have 25% market share, and they're aiming for 50% market share. That was the second quarter this year. And by the end of the year, beginning of 2026, they aim for 50% market share. Now, this is as an adjunct to the GPUs that are going on in these AI compute server data centers. How did that happen?
Well, I think probably again we get back to efficiency, power efficiency. Look, energy is the energy, power, energy. Energy efficiency has become, it's actually more so than silicon efficiency. Designers care about energy efficiency because they're completely power limited. They can't. I mean, think about if you think about take an Intel chip now. If it gets too hot, it shuts down cores on the chip. I never thought we'd get to this situation, right? But that's the reality. The reality is we're running at power levels that make it critical, and the cooling, energy and cooling infrastructure. When you look at a large data center, energy and cooling infrastructure, if you include both the capital cost and the ongoing cost, because if you're cooling, you're getting electricity to run the cooling somehow. That's probably 30%, 40% of the cost of that data center is in that power infrastructure. So if you can make it more power efficient, you can save a lot of money.
Yeah, it's really bad news for Intel, because Intel about 10 years ago had 90 to 95% of the compute server market, and now that market share is dropping precipitously, especially.
It's a run for the money. It's been a great company. It's hard to build great companies that last. It's really hard to build great companies that last.
Well, MIPS had a real roller coaster ride, but we can talk about that afterwards, informally. Let's talk about the new hot RISC technology, RISC-V. What's that all about? Where is that going? And what are its target applications? And will it compete with general purpose processors, GPUs, or any other type of processor?
Yeah, so I think a bunch of colleagues up at Berkeley felt that we should have an open architecture that is freely licensable, and that was their goal, is to create an open architecture freely licensable, and then over time, hopefully, build an ecosystem around that, which would lower the cost, particularly for startups going into smaller markets, where the cost of buying an ARM license would be prohibitive, perhaps. So that's kind of their focus. I think they're making good progress on it. I think the ARM, the infrastructure that ARM's built, the ecosystem they built, is so large and so complete that it takes a while to catch up with that kind of infrastructure and build it out. But they've made a lot of progress, and they've got some good designs, particularly at the lower end, highly embedded small processor kinds of environments.
Now, where are they going? What are the target applications market?
I think it's kind of, there is no single thing, because it's a kind of standard architecture that's freely licensed. So individual companies are going after different markets. So Sci-Fi is going after some things, other companies are going after other markets. They obviously would like to get into the data server market at some point. We'll see.
Okay, thank you. You added DSA, acronym I had never heard of, to our agenda today, John. It's domain-specific architectures. It's a programmable computer architecture specifically tailored to operate very efficiently within the confines of, again, application domain. Now, GPUs, which we'll talk about later, are one example of that. Network processors are another. Can you give us some other examples of domain-specific architectures and what their target applications and markets are?
Well, the big one right now is AI, right? I mean, it's the gigantic. I mean, AI is consuming the vast majority of the computer power within 5 years will be consumed by AI systems.
But isn't AI a souped up version of a GPU?
Well, it's a version of a GPU in the sense that what is a GPU? A GPU is a device that does linear algebra well, the first approximation. And big AI problems, whether training or inference, are a form of a large linear algebra problem.
Now, I'm not sure if you wrote this, or I wrote this, or an AI wrote this, but I have the following. GPUs were developed specifically to operate within the domain of image processing and computer graphics. These programmable processing units found widespread adoption both in gaming consoles and personal computers. With the improvement of the hardware-software stack of both NVIDIA and AMD GPUs, these architectures are being used more and more for the acceleration of massively and embarrassingly parallel tasks, especially Gen AI.
Yeah, that's all true. I didn't write it, but it's all true.
I think you did write that.
Anyway, I don't think so.
All right. So some examples are Google's TPUs,
Yeah.
NVIDIA's NVDLA, and ARM's MLP. Anything you want to add to that?
I think we're getting lots of examples. I think, the good news, deep neural networks are the way you both train them and do inference is by doing a big linear algebra problem. And if you think about graphics is a transformation, right? I mean, the geometry, Jim Clark even called it, right? It's about doing linear algebra.
Well, let me ask something.
By the way, the Cray machines were also linear algebra machines. That's what they were.
Cray supercomputers.
Cray supercomputers. They were vectors. They did vector parallelism. That's sort of what GPUs and TPUs do.
Let me ask you something fundamental. Is an AI processor a GPU with certain neural networks or added features? What is the definition of an AI processor?
Well, you don't actually, for the most part, people don't build the neural network directly. They build a piece of hardware that can simulate the neural network, right? So we're really simulating the neural network by doing linear algebra problems. Right? That's really what they're doing, right? And they like that. The reason that the linear algebra thing is so attractive is doing large matrix multiplies is extremely efficient. You can do it really well, and it has another property at a time when the cost of communication is much higher than the cost of computation. By much higher, I mean 1,000 times more expensive energy-wise to get a piece of data from memory than it is to do, let's say, a floating point multiply, right? So there's gigantic advantage if you can do things that are computationally dense. Lots of computation for the amount of data. Well, think about matrix multiply. N-cubed operations, only n-squared data. So it scales in a way that really makes it convenient to do on these things. And they're power efficient and silicon area efficient.
So XCAT Brain is going to have a question. I think I know the answer, but I'd like to get it from you. Who's actually designing these AI computers? Is it the hyperscalers and companies like startups like OpenAI doing the architectural design, where the actual circuit design and development is done by an ODM in Taiwan, or is it something else?
Well, OpenAI is not doing. I mean, right now you've got a couple of
hyperscalers, Oracle, OpenAI. They all are buying GPUs, but are they designing the computers that the GPUs will go into?
I think they're gonna. I think they'll move in that direction.
Who's designing compute servers? Used to be IBM was king, HP gone, Dell, NVIDIA, Google,
Microsoft, AMD's building processors certainly, and they just signed a deal with OpenAI. So I presume they're going to collaborate on a design of some sort. Amazon, I think.
So hyperscalers, according to my research, do the architecture, but they outsource the actual detailed design and manufacturing to ODMs in Taiwan or in China. Is that the way it's?
Well, somebody else builds it. I don't think they're building. Yes, they outsource the actual construction of the hardware, even if it's their design.
And do the racks and all that stuff. They don't do the
Sure.
design
They
they
don't.
used to do.
Well, they don't build the racks, put racks together and do that, right?
So that's the way it's going to play out, you think? That the
You know, I
computer
think-
companies,
Look,
who's one of the biggest computer companies in the world? Used to be IBM, maybe HP, maybe Dell. They're all gone. Now it's the hyperscalers that are the biggest computer companies in the world,
Correct.
right? Amazon, Microsoft,
Amazon, Microsoft,
they're the
Google.
biggest companies in the world.
Yep.
And they use the computers internally, don't sell them.
They sell time on
Yeah, they
them.
sell time, of course.
Microsoft has a data center.
That's-
a
that's-
very large data center.
That's the essence.
As does Google.
The essence of cloud computing is reinvention of time sharing from 1970.
Yeah,
Okay.
kind of time share.
So we're gonna get back to this AI later on in the program.
Okay.
We have now the version. The version is something that I found very astonishing. Professor Hennessy is one of the leading computer architects in the whole world, and computer science par excellence. Yet he co-founded a company, another fabless semiconductor company that had nothing to do with computer architecture or microprocessor. It was T-Span Systems in 1998. He founded that with a professor from Stanford, double E professor from Stanford University, Teresa, is that correct?
Theresa May.
Teresa May. And that name was changed to Atheros Communications in 2000. It's an extremely successful company from dollars and cents and acquisition standpoint, much more so than MIPS. First product was the world's first Wi-Fi CMOS chip, 802.11a 5 gigahertz technology. That's followed 2002 by a dual band 802.11a/B chip. And company was also innovative in video chipsets, compression to double the performance of 802.11g, MIMO enabled wireless LAN, multiple input, multiple output streams, wireless LAN, expand product, blah, 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 Bluetooth, et cetera, et cetera. Qualcomm acquired the company for almost $4 billion in 2020. Tell us about your journey with Atheros Communication, how you got involved in that, since you were, even though you are double E by training at Villanova,
Yeah.
that wasn't
Not my area.
that was not your area of expertise at Stanford and at MIPS and in other research activities.
Yeah.
How did you get involved in that?
So
Give
my
us insight.
colleague Teresa May came to see me, and she had designed a low power GPS, which was something that the DARPA would be very interested in because they wanted to give GPS to soldiers out in the field. But you couldn't give the soldier GPS and then tell him he's got to carry 10 pounds of battery in addition to his 80-pound bag. So she had designed a low power GPS. So when she came to me, we realized immediately that what a low power GPS was it was a low power radio receiver. You could build a low power radio receiver, then it was possible that you could build Wi-Fi and really make it work. Nobody had tried to do a local area network, wireless network in CMOS. There were some attempts to do it in bipolar, but it was too expensive and used too much energy. And if you were going to use it for mobile, it wouldn't work, right? So we started thinking about markets, and we realized, people were hooking up Ethernets to their and optical networks and DSL to their home, but they had no way to get the signal around their houses. So there was a potential market right there, and we started focusing on that. It wasn't until a couple years later when Intel announced that the next generation of prototype designs for laptops, they were going to include wireless on every design. And that made the market. The market just exploded. I mean, we're a little worried because it meant Intel was going to build their own
That was an Intel,
wireless chips.
Intel Centrino.
Yeah, Intel Centrino, and they had bought a Australian Wi-Fi company, and that meant they were going to have their own chips, but it meant that everybody else building PC clones needed Wi-Fi.
Yeah, the other thing is that
So
was
the market just took off overnight like that.
and that was much faster version. It jumped from like 10, 11 megabits to 56 megabits with
Yeah.
IEEE 2.11G standard.
Yep.
One of the most successful standards of all time for
Yep.
IEEE.
And I still remember the question I asked. Somebody was giving a talk about, they were talking about breakthrough ideas. And the example they gave was if you get Wi-Fi and get the bandwidth up and the cost down, it would be a breakthrough idea. So I went back to Teresa and I said, can we do this? And she said, yes, it'll take us 3 or 4 years to get to that
You must
point.
have been must be a genius to do that.
He's a genius. Yeah. So, you know, it was interesting, you know, when we went to the venture capitalists, and by now MIPS had a successful IPO and everything. We went to the venture capitalists. Most of them said, you're too early. You're ahead of the technology. And they were wrong. They were wrong.
Well, you caught up very quickly. So now we have Wi-Fi ubiquitous in every single device. It's on a USB stick. The streaming, I have it in my TV, the streaming stick.
Yeah.
It's on mobile phones. It's in it's in doorbells.
Yep.
Big doorbell I have with Wi-Fi. And every 18 months, 802.11 comes up with a new improved version that obsoletes the previous version, but they are backwards compatible and they have multiple bands and multiple frequencies. Where is this all going with Wi-Fi? Is it ever going to end? It seems like it's Moore's law on steroids.
Well, I think there was a lot of headroom. I mean, there's a trade-off here because the higher bandwidth protocols don't have as much distance and don't carry as far. So there's a trade-off there that people have to face up to. It's not going to continue forever because you run into various kinds of physical limitations because you are sending signals through the air, right? It's a radio. So
one area that Wi-Fi dominates now in wireless is campus network, but private 5G is targeting that market. You think that's a serious competitor? Private 5G?
Could be. I think there'll be, there's now a lot more integration because when we first started, you were buying a Wi-Fi chip. Now that Wi-Fi processor is a tiny bit of an existing chip, so you're selling Wi-Fi core processors, and then people are integrating the larger thing, including Bluetooth and various other things.
Okay. I hope you people are taking notes and writing down your questions because we're going to have a lively Q&A session when Tom is finished with his presentation. So again, we're going to shift gears to research labs, and you and myself very, very interested and have been involved in research for many, many, many years. In the 1970s, some of the Bay Area information technology research labs included SRI, Xerox PARC, HP Labs, Faircom, where I worked initially in 1970. Intel, very, very strong. Nationwide, we had AT&T, Bell Labs, IBM Watson Research Center. Pretty much all those gone, passé. They've been replaced by the research labs that are in the hyperscalers, like Amazon, Microsoft, Facebook, Meta, and Google. Seeing that you've been on Google's board of directors, which seems like forever, and you've been the executive chairman since 2018.
Just chairman.
And AI told me that you were an executive chairman.
Well, it's wrong.
Hallucinates. Yeah, right. And in any event, not to be diverted from that subject, which is hot for me. Tell us about the research that you are aware of that is not private or confidential at Google, in particular, some of the Moonshot projects, some of the AI developments that you did internally through acquisitions and whatever. Tell us about Google's research from, let's say, 2018 until the present time, last 7 or 8 years.
Yeah, so I think obviously there were lots of ongoing developments, I think, but it's probably about a decade ago that the team inside Google came and said, we want to make AI the core technology behind driving the company forward. It was it was before we had all these breakthroughs we've had now. We had AlexNet, for example, so there'd been some progress in CNNs, but LLMs were still non-existent. And so
LLM is large language model.
Yeah, large language models
with Gen AI and
all the Gen AI stuff.
2022, 2024.
So
2020.
we decided shortly after that to buy DeepMind, right? A UK-based company that was doing a lot of investment in it, built up the Google Brain work to try to get ahead of that. And of course, out of that came the transformer model, which is the thing behind all the LLMs.
And Gemini, what happened?
And Gemini now is a product, right? So there's been a lot of innovation in that, and that's been a core thing. I think it's, there's a change in how these labs work. They don't work quite the same way that they did in an earlier generation. I mean, when there was Bell Labs and Xerox PARC and IBM Research, they were kind of research labs for the country as much as they were for the individual company. But notice that they were built on a particular situation. Each of those companies essentially had a monopoly, right? AT&T on the phone business, IBM on mainframes, and Xerox PARC on copiers. And that's what drove those research labs. The other thing people have observed about them is their most impressive results benefited the industry at large, not perhaps the company, even though, Bell Labs developed this transistor to deal with the fact that switching equipment that was made out of tubes was way too expensive and way too unreliable. On the other hand, the amount of growth and technology built out of the transistor is far bigger than Bell Labs would ever be. Similarly, Xerox PARC never made their invention of the personal computer successful, right? Instead, Steve Jobs went and looked, they got the Mac idea,
user interface and the mouse and all that.
Yeah, which SRI did too as well. SRI did a lot of that work. So it's a kind of interesting. When you think about IBM Research in the 70s and 80s and 90s, it was completely vertically integrated. They invented modern disk technology. They were leaders in semiconductor technology. They were thinking about networking ahead of everybody else. They were the creators of virtual machines. They had all these things, and it's a very different situation today.
Did over AT&T. AT&T was the biggest semiconductor company in the world, and its chips went for internal consumption.
Yeah.
So network systems, AT&T, PBXs, whatever. They were also highly vertical.
Yeah. So the world has changed. I don't know that it's better or worse, but it's certainly changed. Now we have lots of young startup companies. That's a different kind of way to innovate.
Well, what about the Moonshot projects at Google?
Yeah, so the Moonshots are attempts to do things that are bold.
Time remaining.
Well, Waymo, the self-driving car is probably the biggest.
I read that Google lost a lot of money on those Moonshot projects. That was, covered. No, it was covered up.
Yeah, look, we invest a lot of money in it. It says Moonshot. It doesn't say every single one is successful. It says we're looking for something really transformative, and we're going to invest some money and try to find things that are really transformative. And so that's the aim we have. Same thing when we bought DeepMind. DeepMind was kind of a very research-oriented thing in the UK, but we believed the technology was going to be.
Okay, now we're going to go back to AI, and we'll start the conversation with the following. On AI is the answer. Now, what's the question?
Good one.
Do you need help right now, Alan?
Yeah. It's like Jeopardy.
Yeah.
Is an AI going to be smarter than me pretty soon?
It depends on how you define smarter.
Just what's your assessment
Yes.
You're the chairman of Google.
Yes.
And Alphabet. Tell us, what is your assessment of AI? Where is it today?
So I don't know if you saw the two most recent breakthroughs. One was both the OpenAI and the Google Gemini system got gold medal standard in the International Math Olympiad. So gold medal standard, 8% of the mathematicians in the world, no, a small handful of people take this and 8% of them get gold medal. So it's really, really high. I mean, gold medal is PhD level kind of. So they just won another gold medal in a similar programming contest. That was so these systems are getting quite good, and the recent breakthroughs where their focus is on reasoning, not just memorization of facts, right? Memorization of facts. The reason the first generation generative things were so impressive was they could do natural language really well. And if you think about it, what makes us different than any other life form? It's that we have language and we can exchange language, right? So they did natural language really well. That was what was really impressive. And then they memorized lots of things, just because the size of these networks is gigantic. They can memorize lots of facts. But now, in this new second generation, they're doing a lot more reasoning. They can solve complex math problems or complex scientific problems by going step by step through a reasoning process. That's a big step forward in terms of their ability to compete with humans.
And what are your concerns? You had expressed in a previous conversation interview some concerns about AI. Can you share that with you?
Sure. So I have one pile of concerns is misuse of the technology. And I think we're already seeing this with deep fakes and various other things. You know, people using this for cyber
New York
crime.
Times front page today on the misuse in resumes.
Yeah. So I think this is a really serious problem, and we're going to have to mobilize various legal systems and law enforcement to deal with these kinds of things. And it's something very different than they had dealt with in the past, and it can happen at scale. So that's my one concern. I'm not a gigantic believer that there's some existential risk, except with respect to weapons and using AI in weapons and taking humans completely out of the loop, so an AI system can decide to fire a missile or do something else. I think this is potentially incredibly dangerous and could lead to escalation of something which, had a human been in the loop, it would have prevented it. And that's something, the only way I know how to deal with that is we've got to have an international discussion in the same way that we don't allow people to use poison gas, or we don't allow armies to use biological weapons. We're going to need something similar around AI, or otherwise it will become a very dangerous situation.
Last question. You've been here for 38 years.
At least.
Been many Silicon Valley icons during that time. Bob Noyce, Steve Jobs, now Jensen Huang. Who are your Silicon Valley icons? And who are the, let's say, the unsung heroes of Google or other companies that you've been associated with? How about Teresa?
Yeah, Teresa, I think.
Teresa May.
Yeah, Teresa really.
She's an unsung hero.
Yeah. I mean, really amazing work she's done.
You carry.
Gordon Moore, Gordon is one of the. The way I think of Gordon Moore, he has the highest ratio of accomplishment to humility that I've seen by anybody, and he's really remarkable. You know, Steve Jobs was just an incredible person with a maniacal focus on making things easy to use, and really driven to do that. And one of the things I admire about Steve, he overcame a lot of setbacks. He got fired from Apple. He got fired from the company he started, and then came back.
By the PepsiCo.
Yeah. By the CEO he hired. He hired the guy. So, and he came back and
turned the company around.
He turned the company around. Took a while. Didn't happen overnight. unlike the image people have, it took about 7 or 8 years to turn the company
By the way,
around. But
Gordon Moore invented his law before your time because he was at Fairchild.
yeah, I know.
He was at Fairchild. That was before 19.
Yeah, he was originally at Shockley Semiconductor, but that's even before
I don't worry. I wrote an article about it. Okay, last thing is anything I missed that you'd like to share with the audience?
No.
All right.
Questions?
Thank you very much.
Thank you.
Of our session, you can sit down,
Oh,
Joe.
sit down.
My colleague and friend, Tom Coughlin, I thought so highly of him is when I founded the IEEE Silicon Valley Tech History Committee. I selected him as vice chair, and boy, he jumped right over and he became IEEE USA president and then IEEE president last year. So let's give a hand for Tom Coughlin. He's going to give them president of IEEE, the largest tech nonprofit in the world by far. And then he's going to engage in discussion with Professor Hennessy, who's an IEEE Life Fellow, on how to make IEEE stronger and more vital to its membership.
Hi, can you hear me? Oh, yeah. Okay. All right, thanks. So I'm in the last 3 months of an incredible experience being the, so I was elected in 2022. By the way, anyone who voted for me, thank you. I really, I'm humbled to have the opportunity to do this. I've been being IEEE president is a 3-year stage. You're the president-elect, which I was in 23, the president in 24, and past president in 2025. So I just want to give you a little bit of feeling about what this organization is about, some of the things we've been working on this last couple of years. Let's see if I go the right way. Okay. That one? Oh, there we go. So first of all, the mission of IEEE is advancing technology for the benefit of humanity. So, mind way, which way? This way. Okay.
That's pretty.
All right. And so it's really kind of an incredible mission that we've got to do this. And okay, let's do the next one now. For some reason this isn't working. And IEEE, just to give you an idea about the size of this thing, it's the largest technical professional organization in the world. It's now over 500,000 members in over 190 countries. We have about 190,000 student members there. We have 39 technical societies with various fields of interest, 8 technical communities. We have over 6 million documents, over 24 million downloads per month of those documents, over 1,000 standards active and another 1,000 in development, including new areas, including ethics and artificial intelligence and sustainability, various things related to that. We have a whole bunch of transactions, journals, and magazines. We publish a good amount of the world's technical literature. We put on over 2,000 conferences in those 190 countries or more countries. Our publications are cited 3 times more than any other source in patents worldwide, all the 50 major patent organizations worldwide. We have continuing education roles involved in global public policy and ethics. Okay, it is working now. There it is. Okay, so last year when I came into this role, these are the things. Well, these are the things I ran on the left-hand side there. But the average age of the IEEE members, higher grade members, have been increasing. When I came in, it was 51 worldwide, 55 in the U.S. So we needed to increase our retention of younger members. We get tons of students, but they don't stay with us. So how are we going to do that? Well, one of the things was most of those students end up going to work in industry. So if we're going to be able to be here in 40 years and bring those younger folks in and have them be part of us, we have to have value to people working in industry, those involved in the practical applications of technology and the organizations that employ them. I also felt that we needed to increase our outreach to the general public. IEEE, we sort of come from people that tend to be more introverted. And so we even have a hard time telling each other some of the stuff we do, much less telling the outside world. I felt it's really important that we start to do this and do this in unusual ways, where people are interested in technology, be there with them. Also, I felt we need to make new investments in new products and services, in particular the applications of artificial intelligence to all this IEEE content, and then look at developing the future of education. How can we use modern tools, artificial intelligence, and other things to make education more dialed into the needs of the individual learners, to lower the cost, to make the opportunity, particularly to learn technology everywhere by anybody who is capable, has the aptitude to be able to do that. Because technology creates wealth. It creates things that never existed before. And it creates opportunities for people all over the world to be able to help themselves, their families, and their societies. There we go. So one of the things we did last year is we created a strategic goals from 2025 to 2030. So we're now in those, working on those goals now. This is what we want to do. We want to be in service to our mission. Realize that we are a nonprofit and we should be emphasizing some of the things we do for the public good, which we have started to do. Also want to gather all the units of IEEE, have us work together as best we can to accomplish these goals. And we did a lot of feedback and work with consultants on coming up with this. And here are these goals, just to give you an idea here. And I feel that these goals actually are reflecting some of those things that I said, that I was saying we need to be working on. We all work together, all parts of IEEE to do this. And they involve advancing science and technology, engaging with younger folks, engaging with industry, providing, empowering professionals throughout their careers, so that they can be the best that they can be. So, and expand public awareness about the things we do and about who we are and the value we have. So that's these list of, so as the president, I was governing this board. I was the chair of the board of directors of IEEE, 32 people. It's a big board. So we agreed to do this. This year, I'm the chair. The past president is the chair of the Strategy and Alignment Committee, working on how over the next 5 years, with all of the IEEE organizational units, we're going to accomplish these goals. So here's some of the things we've been doing. So we need to transition students to younger professionals. That's what we call students when they first they graduate and they become higher grade IEEE members. Again, we need to engage with industry, and creating a sense of community, I think, is important among us. That we need to work together. We need to get along and find out to push the boundaries in all different ways to understand what goes around us, and create resources that we help our student branches. Maybe help our students to be able to find jobs, interview skills, job fairs where they can't get it otherwise, things of that sort. Also, industry activities are very important. For creating events. IEEE has been very valuable to many academics. But although the organization became IEEE, were founded by giants of industry like Thomas Edison, Alexander Graham Bell. They have not, we've lost a lot of our relevance to industry. I think we need to get that back. And I think we can do that by focusing on a lot more on industry-oriented, practical-oriented conferences and publications, things of that sort, in addition to the research work we do. So, and then also I think providing things that can help people throughout all stages of their careers so that they can stay relevant, so they can become some of the best employees, some of the best people working in their field. Of anybody in the market. So I think this is a thing at the local level we can do, as well as a higher level IEEE. And for instance, local, we work with local companies to do things with them, have events with them, things of that sort. In fact, before COVID, there was an awful lot of being able to get venues and places to meet with IEEE, but it's really hard for our local section to do that now. So we could really use re-strengthening that connection. Go to local trade shows, exhibits and talks, recognize companies for the activities they've done. And I think, again, as I said before, our students end up working there. We need to be there with them. So some other things we've been working on, we started last year to support the CHIPS Act at the international level. And we've had an activity going on in there. We've had events around this. We're Conductor Industry Association. We've created workforce training, for instance, for the new fabs being built in Arizona and elsewhere, to try to bring technology, the manufacturing technology for semiconductors back to the U.S. and also back to other countries where people are doing this. This is really an international phenomenon, and we're continuing to do this work today. We have something called Future Directions in IEEE. This is part of our technical activity. It's actually been one of my favorite parts of IEEE for many years now, where they're looking at what hopefully are emergent technologies and creating initiatives in these areas which span multiple societies. And these may turn into councils or fold back into the individual societies, but they allow us to explore areas and develop new technologies. And I think we need to be doing this. They also make roadmaps. For instance, we have a semiconductor roadmap on all manner of semiconductor technologies, from logic to memories, that IEEE puts on and they publish. And we do this in other areas as well. I've been a chair of a mass storage roadmap, solid state drives, hard disk drives, optical, etc. Roadmap with the IEEE, which we're updating. Our group is updating ours for next year. We're also trying to remake some activities we've started for engaging with companies. And so we started out with something that was kind of rigid, but now we're looking at something that you can tailor a lot more to the individual needs of companies and engage with them and do things that are value to them and to our members who work at those companies as well. So another thing, remember I talked about trying to raise awareness of who we are. The IEEE Medal of Honor, the highest award in the IEEE, is now higher than the Nobel Prize. It's at $2 million.
Who won that award?
It was Henry Samueli,
Henry Samueli.
and he donated it back to Eta Kappa Nu, which is IEEE's honor society.
Good deal.
Yeah, so that's a big deal. And there's other things we've been doing as well. Also, another thing we funded last year was we're calling it a young professional laureate program, where we want to bring together people like John Hennessy and other Medal of Honor winners with younger folks who promising careers and who could be medal winners themselves. We want to embrace that, create relationships between those people, mentorship and opportunities. Something we started at a very small level at this year's honor ceremony in Tokyo, but we're going to be expanding this out in 2027. There's also, here's some of the things we've been trying to reach out to a broader audience, just some examples. We're at the World Science Fiction Convention in 2024 in Glasgow. In August this year, we had a booth and some panel discussions at the World Science Fiction Convention in Seattle. Next year, it's going to be in Los Angeles. We're going to be there as well. We also, this is a slide showing the exhibit space there and some of the stuff we had. We had got some stuff from the History Center, some artifacts that we showed there as well. We also at the Consumer Electronics Show. We're at the Oshkosh Air Show. Has been talking about trying to get to the Paris Air Show. And we also do milestones. Particular milestone at the lower left there was this June in Tokyo, which was the karaoke milestone, IEEE engineering milestone. Indeed. So we've created, it started 2019 in IEEE USA. We created a series of videos which are IEEE is my competitive edge. Some of the original people who were involved in that are shown there, so diverse younger folks. We've been actually doing more of these on a more international level. This last year we finished some in Japan and the UK, and this year in fact, I think the guy's heading off real soon to go to Australia, New Zealand, and Singapore to record more of these videos. They're made for television. And the original ones we used with television audiences. In fact, my wife told me one time, like 2022 or so, or it was anyway. So my wife said she was watching a San Francisco football game, 49ers, and she saw an IEEE ad, and it was one of these. Yeah, that was pretty cool. So we're doing more of these, and they're made in 15, 30, 60 second or 2-second slots, or a few of these run together. They're made for us to advertise ourselves to ourselves for events and things of that sort, but also for the public as well. As I say, they're made for TV by a professional producer. So technology is driving the world's economy. This is the source of, instead of splitting up just finite resources, we can find new ways of turning those resources into opportunities that never existed before. We are representative of the people that do that. And as IEEE, the largest group of doing this, we're involved in all aspects of technology creation and use. Our research of all of our members, our 500,000 people, powers patents, powers innovation in general. We're looking at roadmaps, looking at the future, trying to create the future, and bringing more people in to be part of this effort to advance technology for the benefit of humanity. So with that, I want to thank you for the opportunity to talk to you briefly about this incredible experience I've had the last 3 years.
Tom, no, Tom. Talk with Professor Hennessy.
Of course.
Have a little chat.
Or we can open up the floor.
You want to open the floor?
I think we should open more, but first I got something for you. So I made some coins, and I'd love to give you
Wow, great, thank you.
also one for you.
Thank you.
And I've got one for you, Sandy,
This is it.
for helping us.
Andy,
bring
you
this
did a
together.
yeoman's job. Is this on? Can you all hear me?
You have it? Okay, all right.
Not a Bitcoin. Not a Bitcoin.
Not a big
I'll be glad to sit and join you guys.
So again, we have two different sets of questions.
the person.
We're gonna take live questions, so I'll moderate. And then Jeffrey Paulin, my friend Jeffrey Paulin is on Zoom. Is that correct?
Yes.
And he will moderate
Yes, I
the
am.
Zoom question.
Okay.
And please, tell me who your question is directed to. It could be either myself, Professor Hennessy, or Tom.
Professor Hennessy, of course, I have to keep his honor, but all three of you are welcome to answer.
Microphone closer so we can hear you.
Okay, I'm Dr. Afzal Hussain, and my background is actually directly your area, the CPU architecture. My primary concern is the power consumption. What happened is that a lot of silicon-based people thought it was inexpensive. They started using it, never really paid attention to power consumption. And knowing your knowledge of the linear algebra, the large systems, what is the right way to go for efficient linear algebra handling and sparse matrix and that kind of thing?
I think, look, the game has shifted where one has to look at measures like performance per watt as the kind of key driver, because energy and power is the limit. And now you have to look at overall system performance as well, right? Because the problem with trying to take that metric is you can't just measure that by what it costs to do a floating point multiplier and floating point add. You've got to look at a total system performance model. And it gets more complicated if the memory model gets more complicated as well. So if you have sparsity, for example, or something like that, that's going to make the memory model a lot more complicated in terms of performance. So I think it's going to be, the design challenge is going to be hard. And what we worry about is that we may be near the end of the curve in terms of getting increased performance per watt. We've managed, but it's slowing down. If you look at performance per watt, it was getting better and better and better, and now it's starting to turn the curve and begin to plateau. As that plateaus, our problem is going to be, if we want more computer power, we're going to have to find a different way to get it. And that's going to be either breakthroughs in algorithms, maybe some new technology, maybe something that can do heat removal so we can stack 3D stacks with not just memory chips like HBM, but actually stack memory chips and hot processor chips in the same stack. Figuring out how you cool that beast is going to be one of the things we're going to have to look at.
Dan?
So I'm Kevin Parnell, Professor Hennessy. I'm Vice President of Silicon Valley Engineering Council, and I was at Stanford right around your time. I started 1980 to 84 for my PhD.
You're a mechanical engineer.
I'm a mechanical engineer, but these breakthroughs that you did have had a huge effect on my career and the things that I could do in terms of computer modeling, binary element modeling, things like that, the graphics. We sucked up all the stuff that you did in the companies that I was with, that failure analysis and Exponent. We used all that XTI equipment. I was just going to make the point. When I first went to Stanford, I had to go to the IBM Computer Center and use punch cards. Then I went to digital equipment stuff, and then to VAX and on that. So I really followed that whole thing into the IBM computer, into the personal computer and everything. What you did, absolutely incredible. I mean, I think it really did raise what all of us in mechanical engineering and aerospace engineering, it had a huge impact. You're recognized in IEEE but this other stuff is really amazing to me. I think it's wonderful what you've done. The other part I wanted to ask Tom, known Tom a long time, voted for him multiple times. Yes, I'm a mechanical engineer, but Tom is really the one who got me involved with IEEE at the section level, at the chair, and things like that. So I think multidisciplinary stuff is the most important thing anymore. You guys have made the point. Yes, power, energy, heat. Well, those are kind of mechanical issues, and we have to help with those. And those are really big deals. So Tom, with you, totally agree on student members, keeping them in. I think that's been a real problem. It's a real problem in ASME also there. So I guess some of the things that I wondered about is, are we doing well with both female and male students? Are we doing about the same, or are we better one way than the other?
So is your question basically on gender within IEEE?
Within student members and advancement of student members. I mean, I know we're getting old in IEEE.
No, that's not the question. We've got to inculcate student members so that they continue.
Exactly
Many
right.
student members just drop out.
But that's my question to Tom is, what are we doing on that in
I
terms
think
of men and women?
I think the female members of IEEE are something like 20% or less. I think that's right.
How about students? Similar?
It may be similar. It depends. I think it sort of follows the demographics.
Yeah, I think we're missing out then, because I mean, Georgia Tech
yeah.
now, women are almost 50% of the population at Georgia Tech. When I was there were about 5. So
And we
we're
have the
missing out.
WIE. We have the WIE.
Yes. Yes. No, I mean, and IEEE has wants everyone to be able to participate in these technologies. It has allows anybody with the aptitude to be able to make a difference and to do incredible things, whatever their job is.
But more broadly, what is IEEE trying to do to encourage student members to retain their membership? Because there's a huge increase in price between student IEEE member and regular IEEE member.
Yeah.
What are we doing to
It's less than
encourage them to maintain?
it's less than your cable subscription.
That's right.
Yeah,
That's
but
right. And more important to your career.
that's exactly right.
So what are we doing?
There's a lot of resources in IEEE that are available for people to be able to participate. For instance, by being volunteers, you learn leadership skills, and so knowing something in depth about a particular subject is how we generally start out. But over time, you've got to be, what you know about that subject is things are going to change, or it may not be as relevant. And so you need to have the capability of broadening your interests, broadening your knowledge of things, and to be able to work with other people to get things done. Because we are human beings, and we do have to work with each other. Understanding the ways in which we can work better with each other, learning leadership skills, learning how to get people to have confidence in you and want to work with you on things is really important. And so IEEE offers those kind of opportunities. For instance, if you become a leader, become a volunteer without getting fired. Basically, you can make mistakes. It's a way to learn things as long as you have a good attitude towards things. And so as a consequence of that, I think those are some of the values. I think also that we're trying to increase our engagement with practical application of technology and with things that have value to companies, working with companies on getting important things done and on the people that work with them. So I think there's a lot of things that an organization like ours can offer you. Plus, I think just the pride of being part of something that has had so much impact on the world as what the IEEE and the people in IEEE have had, like us. I mean, like you, for example.
Well, John, as an IEEE Lifetime Fellow, what would you recommend IEEE do, and your advice to Tom on how to strengthen the organization?
Well, I think IEEE does great work. I think the challenge is to keep young people. I joined as a student member many years ago. And then you get a life member once you've joined long enough. So
You have to be 65 to be allowed.
oh, you have to be 65. Okay.
Well, plus 100 for your
It
years
has to
of
come up
service.
to 100.
They have to grade.
It has to come up to 100.
Right.
So I make that level.
Me too.
You're forgiven.
So, but I think, trying to figure out how we make it attractive. I mean, and the issue, we have to do a better job of attracting women into electrical engineering. We do not get the highest marks. There are some of the other engineering disciplines and some science disciplines that do a better job of it.
Mhm.
So I think that's something we could all,
I agree with
work
that.
on.
How do you promote IEEE at Stanford University? Or are you doing that already?
Students do it already. They do it. They're pretty active. That's certainly my experience when I was an undergraduate. It was my fellow students who got me involved.
Actually, the
I don't
student
know.
branch, we're just trying to reconstruct it again.
Oh, okay.
Yeah.
Yeah, there's a little problem there.
After
Okay,
COVID.
other questions?
COVID, yeah.
Other questions for the audience?
One over
How many
there.
questions?
Yeah.
Well, let this gentleman ask a question. Andy, do you have any questions on Zoom? Okay, so we'll take the question from the gentleman at the mic, and then we'll take the questions from Zoom. You got it, Jeff?
I actually had two questions, but let's see if we can get to that. So basically, on an AI implementation.
Put the microphone closer to your mouth, please.
Yes,
We can hear you.
regarding AI implementation. So you mentioned that the linear algebra problem and it's done on GPU. I was wondering if you can implement why just not mapping to a hardware, a neural network to a hardware which looks like a neural network.
I can hear.
Which directly implements a neural network?
Yes.
You could. You could do that. I think understanding the parallel. Well, first of all, the neural network is really big. I mean, think for these modern next generation generative AI models, 500 billion parameters, right? So you're not really going to implement it as a strictly neural network in conventional silicon technology that way, because the number of transistors you need would be phenomenal. So in fact, what's done is a translation of that to an alternative structure that represents it. The closest thing to that model, the closest thing are the companies out there doing graph-based models. That's the closest thing. GraphCore is probably the best known example. But Service is trying to do something similar. There are a couple companies out there trying to build these graph-based models, which do something much closer to representing the neural network directly. And the interesting thing about this is, look, neurons are a lot more complicated than the artificial neural networks that we model. They have much higher fan out and fan in. They have a more complicated signaling mechanism. That's what makes the brain so efficient. Remember that brain is about 20 watts of power.
Right.
One of these data centers is 1,000 times that energy level. So there's something, evolution designed something really amazing in our brains. And my guess is one of the interesting problems that there are some researchers working on is, can we get more inspiration from the structure of a human brain and therefore get much more efficient than the current AI models that we have? But that's a research question still.
I see. Okay, so this
This gentleman there. You ask your question, then we're going to take the Zoom.
Oh, I have three questions. I hope I could get an answer.
I'm going to let you have one and then.
Yeah.
One? Okay, well,
Are they all for Professor Hennessy?
yeah, so Professor Hennessy, yes. Great honor to speak with you, Professor. You're a legendary person in the field of computer architecture. I bought your David, Patterson Hennessy book, the undergrad. I used that for my education. So thank you for writing the textbook about the MIPS process. Anyway, my question I have is, you alluded to, I came a little bit late, so I only heard portions of the talk, but you mentioned that CISC architecture started to add instructions, those lowering performance. And you mentioned that they not really meant for high level language based software development. I assume you mean C language.
So easy.
Isn't it true that in practice in the 1990s, starting with 486 processor, that the burden of adding these complex instructions became less of a penalty to the CISC architecture due to Moore's law making transistors cheaper? So the notion that complex instruction lowers performance is not really true in practice. In practice, it's still in the x86 architecture, but they're sort of like put in the microcode ROM portion that is not recommended for use, but it can still get used. So isn't it that is not really true in a sense that it doesn't really lower performance. It's just like some legacy stuff you have to still support. So isn't that kind of not?
That doesn't necessarily lower performance. I mean, the other thing that happened was the design of with the Pentium Pro, for example, and with same thing happened on the VAX 8500 series. They went to a different style architecture where they basically have an instruction cracker that takes their more complex instructions and breaks them into simpler instructions. And then the back end, then they float those simpler instructions to something that looks much more like a RISC back end that's pipelined and everything. I mean, part of the problem is these complex instruction sets, building a pipeline for them is just too complicated. It's just too hard to do. So that was the right solution to that. And then it's just an overhead question, an overhead of this kind of microcode store instruction cracker. And that's an overhead issue. It's some performance, but the performance number is probably smaller than the silicon and power overhead.
Second question. You're one of your famous students.
Okay, let me stop you.
Sure.
Yeah.
A question has a question mark at the end,
Oh,
That's right.
right? So be very, very brief. I'll let you ask one more question.
Sure.
But ask the question, don't make any statement.
okay. One of your famous students was Pat Gelsinger, who studied under you, if I remember the same.
He was a master.
And he was saying, he was disputing the RISC proponents at a time who were saying that you can't do better than around one CPI per instruction. Once you couldn't crack one CPI of 1 with x86 was touted by the RISC proponents, but Pat, who was at the time like 32 years old, was already doing that with 46. So wasn't this the case where your student was maybe disputing the RISC advantage or the assertions that we're making? So what is your, what should I say, comment or your thing about?
Pat worked for Intel.
Right.
So Pat was going to say the Intel line, right? And anyway, it's a lot more complicated than you illustrated. I mean, getting more than one instruction per cycle is a challenge for anybody. And lots of things make it difficult to maintain rates below that. But lots of processors have done it now, right? It's just the biggest issue right now. I mean, the reason that we stalled on general purpose performance improvement, you look at the last 8 years, processor performance going up by between 5 and 10% a year, 5 and 10% a year, after a period where it was going up by 50% a year. The reason is that we've used up all the key ideas that work for general purpose processors. And you look at the new Intel processors. I mean, they have to launch gigantic numbers of instructions and try and keep tons of instructions in flight to try to get the performance up.
Well, performance is increasing only by means of semiconductor technology, not because of new architecture.
Yeah, I mean, there's some, of course, what do architects do? Architects use improvements in semiconductors to turn into more performance. But you're right. The performance is very limited, which is why all the people doing AI are going to embedded accelerators, DSAs.
Okay, now we're going to move to Zoom. Andy?
Thank you. Thank you. Can you hear me?
No.
Are you able to hear me?
Why don't you give me a microphone and I will read the questions.
Right, yeah.
Oh, it's on the screen?
I have 3 questions in chat.
He needs a microphone.
Probably in chat.
All right, so one of our questions for Dr. Hennessy is, can you please describe the top 2 guide rail regulations AI developers will need to be held accountable to ensure alignment with human prosperity?
Well, human prosperity is a big thing. So the first thing is, I think the first thing is enforcement of current laws, irrespective of whether AI is used or not. So, for example, if a doctor makes a mistake in diagnosing something, you can sue for malpractice, right? So the same thing. If an AI system is advertised as providing some functionality and it doesn't provide it, then you need to be able to sue for it. And we need to get comfortable with that because that's going to be critical in deploying these technologies. I think the other one is more subtle. It's a guidance rather than a guardrail. And that's try to focus on the development of AI systems which enhance human capability. Not simply replace it, but enhance it. And there's a recent study which I really found interesting, looking at medical diagnosis, where they did a study of, they compared diagnosis by a physician alone, diagnosis by an AI system alone, and diagnosis by a physician with an AI system to support him or her. And it was the combined event that got the best insights most quickly. So that's a good example of how do you augment human capability. And if we can use AI systems to augment them, to do the kinds of things you don't want, look, I teach. Well, I love teaching. I love working with students. I hate grading.
Yeah, there you go.
So an AI system that can help me grade and that can do some of the record keeping and that sort of thing, that would be great. So that's the way I think about it.
I don't know any university lecturer or professor that like grading. We all hate it.
Exactly.
Yeah.
Okay, next question.
Oh, this next one. This fellow, John Massey, has a question.
Oh, John, my good friend, John.
Can you comment on lessons learned from MIPS and other companies that you could apply when Stanford president?
Oh, my God. Yeah, so I think, know something about a business before you start it probably is a good start. Then I think put all the wood behind one arrow. One of the mistakes we made at MIPS is we got infatuated. There was a period where there was an alternative ECL technology that was developed that you could get higher clock rates potentially.
Yeah, but that was a power hawk, emitter coupled logic.
Yes. But there was a lower power version of ECL by a startup company, and we got interested in it and tried to use it for something, but it was a mistake because it took us away from the core technology and slowed down the development of the next generation CMOS technology. We should have just stuck to our knitting and focused on that, and that would have been a lot better. I'll tell you, the other really hard thing about MIPS was we needed to invent both a new technology and a new business model because there were no fabless semiconductor companies when MIPS started. It didn't exist yet. So that was, don't ever do that. If you have a startup, decide you're going to.
Not only that, selling IP cores.
Yeah, selling IP cores, the same thing. There wasn't a fabless. So business model innovation with technology is well understood, or technology innovation. If you have to do both, it's really difficult and hard and takes a long time.
Like you pointed out, in the days before, like 1984, when we founded MIPS, if you were designing semiconductors, you had to have a fab.
Yeah.
The AMD guys say that you weren't a real man unless you had your own fab.
Yeah.
Next question.
Yeah. So, Dr. Hennessy, it's been 20 years since the last revolutionary as opposed to incremental change in computer architecture and organization. What will be the next fundamental leapfrog technology in computer architecture and organization, and when will we see it?
You do it.
If I knew the answer to that question, I'd be investing in it. I'm not. The honest answer is I'm not really sure because I think clearly there's some things about in packaging that could be. I don't know that they'll be quite so transformative, but they could be very helpful. I wish I knew what the replacement for silicon was. Because eventually silicon's going to run out of steam, and eventually isn't that far away, especially for the young people in the room.
Okay, we'll take two more questions, but again, be brief.
Yeah.
Questions with a question mark at the end.
Well, this guy had a question.
Go ahead.
I had a question for Dr. Collin. You mentioned
who?
For me, I think. Is that right?
Coffin.
Yeah, for Tom, that's fine.
Sorry.
Yeah.
You mentioned the issue of retention for young people.
Yes.
And as a member of the IEEE board at Santa Clara, I wanted to ask, what is one thing you wish that all student chapters would do to help with this issue?
That all student chapters.
All student chapters would do to help with the issue of the retention of young people.
Let's see. So I think there's a number of things that I think. One is to be informed about what the IEEE is, you know, and to teach yourselves or let people come in and talk to you about the things that IEEE does, the various things that you can do in the organization. I mean, we do everything from make standards that things run on to, you know, developing new technologies, but also I think we can be a great value to people working in industry. So I think there's things you could do for yourselves, you know, as part of IEEE, helping each other or bringing in people maybe from the IEEE, local IEEE can help on writing resumes, how to do interviews, things of that sort.
Mixers.
What's it?
Mixers, parties.
Mixers, parties, things of that. Yeah. I think, and our section should do a better job going out to the university chapters.
Our section means Santa Clara Valley.
Yeah, Santa Clara Valley section, which you're part of. I tried to do that some over the years, but I think we could do a lot more of that, and to engage with the students, letting them know who we are, what we are, and that we want them to be part of us, and the value that can have in doing that.
Okay, last question.
So question to all three of you. You've watched Silicon Valley grow and change since Shockley Laboratories. Where do you think it's heading today? In terms of significance, IEEE has.
Where is Silicon Valley headed today?
It's grown to be a global organization. It's like a lot.
I mean, it remains the center of the technical world in computing, information technology, semiconductors. I think the challenge is going to be, if we can't solve problems of transportation, problems of housing in this area, we are eventually going to enable somebody else to build a competitor to those things. So those are the kinds of things we need to really focus on. The other thing I'd mention is, one of the reasons the Valley is so great is it's brought talent from around the world. Yes. And if we stop importing talent from around the world, we will lose our position as a leader in the world. And you just have to go around this valley.
That's already happening with the big increase in the price of H-1B visas.
Yeah, H-1B visas, reduction in the number of students from India is dropping by 20% in 1 year. I mean, these are worrisome things, I think, and it's gonna undermine our ability.
All right, Tom, you go next.
All three of you.
No, I'm going to go last. Tom will go next.
So what's the question again? It was
about. The question is, what's the future of Silicon Valley? Thing? He said the question is for all three of us. You can go.
Yeah. Next. So you know, I agree with the
moderator. All the first to speak.
Okay. I agree with you on the issues that, you know, this place has been built by people from everywhere. You know, and that's made a big difference in terms of the visions and ideas. And the communities we have here. I mean, we have food from almost everywhere you can get here. You know, so we've got a lot of culture here, in fact, a mix of cultures, and I think that those bring up new ideas and new ways of working together. I think, but we're also on the edge of technologies that are, or new opportunities that go on where we've been, and one of those is what's going to happen when people start doing more in outer space. You know, and that is beyond just Silicon Valley, but it's like, in a sense, I think of Silicon Valley as it's kind of like Camelot or something like that. It's a place where magic things can happen. And if nothing else, I think that this way of doing things, this way of making things happen by people from everywhere, can happen in other places as well. And so, you know, I hope that we will see that there's possibilities here of continuing here, and I'd love to be able to do that. I like the weather, a lot of good food and other things here. But there's possibilities of doing this elsewhere as well. As I said, one of the things about IEEE is we would like everyone who has the aptitude and the interest to have the opportunity to participate in the kind of things we do in Silicon Valley, wherever they are. So I think there's value in Silicon Valley, there's value in possibly in other places as well, if they can follow if they can do something like what we've done here, and maybe do it even better.
My take, I lived in Santa Clara, city of Santa Clara, 55.5 years. So I've seen all the twists and turns and ups and downs. The transformation from semiconductors to PCs to peripherals to the rise of the cloud companies and hyperscalers, and now NVIDIA and AI. And having seen all of this, I think the greatest risk in the technology is concentration and dominance. I think that cloud hyperscalers and their associates have way too much power. And I think that risks shutting out a lot of startup companies and a lot of new innovation. That to me is the biggest risk. With that, we're going to close the session now. Thank you all for coming. I hope you enjoyed the session. There's no more questions. The time has expired. To talk with us informally afterwards. We'll be here for a few minutes. Thank you all for coming, and I hope you enjoyed the show.